I welcome you all to another lesson session on finite element procedure. Today we are going to solve this problem using ANSYS software. Uh, I actually solved this problem using and calculation and finite element procedure on MATLAB in my previous video. So you can check the previous video which I posted to understand the first principle calculation about this problem. So in this lesson today, we are going to solve this problem using the ANSYS program. We have a structural body in which a point load is applied at the center, a point load which is noted here as P, coming, which is noted here as P as 60 kilonewton or 60 times 10 raised to power 3 Newton. And we have a structural gap at the end of the structural body at node B between the body and a support, a wall. And the structural gap is 1.2 mm. So we are going to model this gap for this particular problem on the ANSYS program. The body, this problem, we are asked to analyze this problem using two linear finite elements. Finite element 1, finite element 2, and the structural body has three nodes. Node 1, node 2, and node 3. And we should also apply a 1.2 mm gap at node 3. So I'm going to show you how we solve this problem on the ANSYS program. I'm not going to waste time on the ANSYS program in the geometry modeling of this particular problem because I've done this several times in my previous video. When we move to the mechanical interface, where we start specifying our boundary condition like the support and forces on the structural body, that's when I will talk a lot. So let's move right to the ANSYS Workbench work environment. So this is the ANSYS Workbench work environment. So the first thing you need to do, you need to drag your static structural solver to the middle of the screen, which I just did. And we need to define our material property. I'll do that quickly. I double click on engineering data, click new material, create new material. I term the material steel. You can give it any name you want. So I'm naming it steel. I will add a linear elastic property to the material isotropic elasticity, and I'll define the Young modulus and the position ratio. You will see in the question that the Young modulus is 20 gigapascal or 20 times 10 raised to power 3 Newton per millimeter, or 20 times 10 raised to power 3 Newton per millimeter. So I'm going to enter this value in the Young modulus. I'm going to enter the Young modulus on the ANSYS program. So first I need to change my unit to gigapascal because I want to enter the unit, the Young modulus value in gigapascal, 20 gigapascal. The position ratio, although I'm not given the question, we can assume a value for this. Typical position ratio for steel is 0.3. So I will enter my position ratio as 0.3. For one-dimensional problem, the position ratio does not actually affect the solution of one-dimensional problem. But if I don't specify this value, I won't be able to run analysis on the ANSYS program. So it's compulsory we specify this value, but it does not affect the numerical solution of our results. So now that I've defined my material property, I'm going to close the engineering data and I'll move to the next workflow. The geometry, I will double click on the geometry to open the space claim working environment where I can define my geometric model. This will take some time. Oh, I forgot to do something. I did not activate the line body, which I was supposed to do. Oh, and I was not able to do that. So once the space claim working environment opens, I will close it to activate my line body. It's very, very important you activate line body when you are carrying out a one-dimensional analysis. So when the space claim opens, I will close the space claim so that I can activate that line, so I can check that line body in the table here. The space claim has opened now, so let me click on it. So this is the space claim working environment, but I need to close it so that I can activate the line bodies. So now I check the line body. I will double click on it again to open the space claim working environment. So it has again started. I'll open it. Now I'll define my geometry with two finite elements. Click on this button. I will select the XY plane, bring it to view. I'll use the line command to define my two finite elements. The two finite elements, the length is 150 mm. So from 0, coordinates, I'll draw a line 150 mm, enter. $150 enter. I will press escape to leave the line command, end sketch to leave the sketch command. Now you need to define your cross section. Go to the prepared tab. Under the beam panel, the profile, click on rectangular cross section. I want to create a rectangular cross section. In our question, we're told that the cross sectional area is 250 mm square. So let's define if the cross sectional area is 250 mm square and we're using a square, so the length of our square will be square root of 250. I need a calculator. Oh, this takes some time. Calculator. So 250 square root. It gives us 15.811 something. I'm going to copy this value and I'm going to apply it to the cross section which I just created. I will did the beam cross profile. I need to change the B and H to 15.811388. I copy and paste the value for B. I'll do the same thing for H. Click on 10 mm, paste, enter. So you see B is 15.81 mm, H is the same thing, 15.81 mm. So I'm going to close this tab here and I'll go back. I will press escape to leave the create, to clear any active command. Click on structure, go to profile, rectangular. We need to apply this rectangle cross section to our line body. So you click on create. Now, because rectangle is selected, we can apply the rectangle profile to our line body. So I'll select the line, the first line. I'll also select the second line. It's taking some time to apply cross section. Computer is not responding for a while. Okay, I've applied the cross section to the two finite elements. So what you need to do now, you need to press escape on your keyboard to leave the create command and go to the beam folder which just appeared on the left hand side of the screen, and on the first finite element beam, define the type as link or source. Also do the same thing for the second finite element, define the type as link or source. We need to also do one more thing. We need to go to the design folder here, and we need to change share topology from none to share. Very important. Now we can leave this space claim working environment. We have defined the geometry of our finite element. Now we can leave this working environment. Good. Now we double click on the model workflow tab to open the mechanical work environment, where we will define our mesh, the boundary condition, and we retrieve results, solution from the ANSYS program. Take some time. So the work environment is active now. So I'll move through the workflow from model, geometry, material till I get solution. Under the geometry, we need to apply our material property which we created to the geometry, to the finite element. We have one finite element defined in the geometry, but you should know that this one finite element is a combination of two segments. You see the first segment here, second segment here. So the two finite element is grouped under one part in the geometry. You should note that. I've selected the parts. Now I will apply the new material I created in the engineering data workflow. So I've applied that material as steel. Under the material, you don't need to do anything here. This is just a list of materials available to be applied to our finite element. Under the cross section, we don't need to do anything here. Under the coordinate system, we don't need to do anything there. Under the mesh, I will enter 150 as my element size, because that is the least, that is the greater or greatest length of my parts. So I enter 150 because I want to force the ANSYS program to solve this problem using two finite elements. So that's why I'm entering 150 mm here. Under the element order, I'll change it to linear. So that's all about mesh. Let's go to the static structure, where we define our boundary condition. Now let's create displacement support. Click on the static structure, insert displacement support. So a displacement support has been created. We apply displacement support to the node. So I've select node 1, and I will apply the displacement support to that node. And I will define the displacement quantity in the x, y, and z component as 0, 0, 0. We also have a support at node 3, but at node 3 we have a gap of 1.2 mm. So we create another support. I'll just duplicate this support, and I will select node 3. Node 3 has been selected, and I will apply this displacement support to node 3. In the x component, my x component is not 0. My x component is the structural gap. So I will define this as 1.2 mm from the question. My y, I want it to be 0, but my z, I can set it as free or 0. I will leave it at 0. For the node 2, I need to prevent movement in the y direction. So I will also create a new displacement support. Duplicate, and I will apply that support to node 2. Apply, and the y direction 0. In the x will be free, and z also will be free. X and z are free to move. So since now that we have defined the support for all the nodes, we can now define our load. Based on the question, we have a 60 kilonewton load applied in the middle of the structural body. So I'm going to apply that load now. So under the static structure, right click, insert, click on force. So select the second node, apply the force to that second node. We are defining the load by component. So select component. In the X direction, the force is 60,000 Newton. 60,000 Newton, good. In the Y and Z is 0, good. So now we have defined the force on the body, the force acting on the body. Now we can add solution to the result before running the analysis. In my previous lesson, I normally run analysis before I add solution to before I add the solution that I want to visualize. But I'm going to add it now. So you right click on the solution, insert, deformation, directional. The orientation is in the X direction, as we see here. So we do for area force too. Beam result, area force, good. We also probe our force reaction at node 1 and node 3. So insert, probe, force reaction. I actually need two force reactions, so I will duplicate this force reaction. The first force reaction, the bonding condition, I want to attach the first force reaction to displacement support. And the second one, I want to attach to the displacement at, I think, node 2. Did I define it properly? It's weird. Node 2, node 3, node 2, okay. Force reaction, displacement node 2. We're supposed to show force reaction node 2 at force reaction 2 at node 3. I don't know why it's not showing, but let's run analysis and see what happens. This will take like 1 minute. Wow. Okay, 8%, 10%. %. Good. So the directional deformation we see. I should use this is the color plot of the directional deformation in the X direction. So we see that the deformation at node 3 is 1.2. The deformation at the middle of the member of the structural body is 1.5, which is what we got in our ANSYS calculation. I will show you. And the deformation at node 1 is 0. Let's go 0, 1.5, 1.2. Let's check our PowerPoint, our manual calculation in our PowerPoint. So you see the deformation as a 1.5 at the middle at node 2, and because there is a 1.2 mm gap at node 3, the deformation at node the allowable deformation at node 3 is 1.2. So that's why we have 1.2 at node 3. That's why we have 1.2 at node 3. We can animate this color plot by clicking on this play button. So you see the 60 kilonewton force is dragging the structural body to the right continuously. So this is the deformation under the 60 kilonewton load with a 1.2 mm gap at node 3. Let me stop this. To the area force, we see this is the color plot of the area force, and we should use the probe. We'll see that this red color, the value is 50,000 Newton. That is 50,000 kilonewton, and 10,000 minus 10,000 Newton. So if you divide this value by the cross-sectional area, we'll get the normal stress in each of the parts. So 50,000 divided by 250, I think that is about 200 megapascal. While 10,000 divided by 250 is about 40 megapascal, which is what we got in our hand calculation. So the way we model this, it means that the way we model this problem on ANSYS program is very, very correct. We are getting the same answer with our hand calculation. For the first reaction at node 1, I can display the result in a tabular form. The first reaction in the x direction is, we see it here as minus 50,000 Newton, pointing to the left, which is what we also got in our hand calculation. And at node 3, it is 10,000 Newton, minus 10,000 Newton. First reaction, 2 in the x direction, minus 10,000 Newton. So the result is exactly the same with our hand calculation. So that means we model this problem appropriately on the ANSYS program. I want to explain something to you before I end this lesson. I applied 1.2 mm deformation at node 3 and 60 kilonewton force at node 2. The effect of this boundary condition, actually, in my hand calculation, we calculated that applying a force at node 2, we need 40 kilonewton to cause a 1.2 deformation. So when I apply 60 kilonewton force at node 2, a part of it, which is 40 kilonewton, moves the node 2 by 1.2 mm. And also, as the force is moving node 2 by 1.2 mm, the deformation I placed at node 3, which is 1.2 mm, is also being shifted. The overall effect of the 40 kilonewton force and the 1.2 mm deformation at node 3 is to cause a stress in the first finite element, and however, there won't be any stress in the second finite element, because 1.2 deformation is placed at node 3, and also 40 kilonewton, which is equivalent to 1.2, is also placed at node 2. So they move together, causing zero stress in finite element 2. The stress in finite element 2 is caused by the remaining 20 kilonewton force. So it's the remaining 20 kilonewton force that actually stresses finite element 2 and finite element 1. So this is the explanation of the boundary condition. Why I apply the boundary condition in this manner in the ANSYS program. I tried actually several combinations of boundary condition. This is the only one that worked. I tried one interesting boundary condition which did not work. I actually placed a 1.2 mm deformation at node 3 and a 1.2 mm deformation at node 2 because they move together. And then I reduced the load at node 2 to 20 kilonewton. But I did not get accurate results. Why I did not get accurate results is after the body has been deformed by 1.2 mm, after final element 1 has been stretched by 1.2 mm and the final element 2 on stress, the 1.2 mm deformation at node 2 is still applied, and the application of the 20 kilonewton force does not stress the second finite element because node 2 is not free to move. It has been fixed by 1.2. So that's why that method did not actually work. So the lesson here is that you should try to actually find a way of validating your results when using finite element software. You can be very, very tricky. You can model something. If the boundary condition you define is not correct, you get abstract results. So that's why understanding the first principle, manual calculation, or using a simple form of validation is very good. It's very good when applying ANSYS program to solve structural engineering problem. So in my next video, well, I'm going to solve one more one-dimensional problem. It's actually an angle problem, like two angle bars. Let me show you. That is the last one-dimensional problem I'm going to solve. Then I'll move to another structural element design type using finite element procedure. So we're going to solve this problem in my next video tutorial. So thank you so much for taking the time to watch my video. I hope the lesson session has been very impactful on you guys. See you next time in my next video. Bye.